Oh, hi. So the question is that you have this vector field f of x, y, and z, and it's given the components are given by x plus y minus 2z, x plus 2z, right? And then you have this surface that is formed by the two equations z equals x squared plus y squared and z equals x. And then this is oriented such that the curve that is created by these two surfaces go in the counterclockwise direction when viewed from above. And you're supposed to find this line integral using Stokes theorem. Okay, so just um, uh, before we start out, let me state the Stokes theorem. So when you have this equation where the curve is when you want to find a line integral or a vector field, we want we apply Stokes theorem in this fashion. So sigma is the surface that is created by this curve. We will explain that later. And then we take the curl of f and we take a normal vector to the surface and we do this surface integral, right? So this is what is called Stokes theorem. And to give you a quick heads up why we are going to use Stokes theorem here, because it seems like we have this line integral which is just a line integral, and we just expand this up to a surface integral, which looks much more complicated than what we started out. So in the process of working this problem out, we 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 need to find the curl of f. So let's start with the curl of f, and then it will be clear why we want to use this Stokes theorem. Okay, so curl of f, um, sorry, curl of f is basically a determinant. So these are the components I, j, k of, and then we write down the partial derivative with respect to x, the derivative with respect to y, and the partial derivative with respect to z. And we write down these components x plus y. So this is the I component here, and this is the j component. We this down here to z and k x plus 2z, right? Okay, so now we just need to find this. So for I, we just find the partial derivative of this. So we don't have any y here, so that's 0. Now we subtract the partial derivative of this component with respect to z, and that is -2. And this is a y component. And negative, so the j component is negative. We start out with negative. So let's just erase this part. And for the j component, we find the partial derivative of this with respect to x, that is 1, and the partial derivative of this with respect to z, that is -0. So this is j. And for the k component, we have, let me just erase this. We just need to find the derivative of this, which is 0, because there's no x here, and partial derivative of this. And this is just 1 here, -1, because k, right? Okay, so let's see what we get here. So 2i minus j minus k, right? So the curl f is, this is much more simpler than f itself. So this is much more complicated. So curl f is just a bunch of constants. So that's why we would want to go for uh, this Stokes theorem using the curl. Okay, so now we have like worked out this function. So let's think about the parameterization. So now this sigma is the surface. So let's look at the surface we are talking about. Let me draw this. So we have the z component here, and we have the y component here, and we have the x component here, right? So this one here, let me draw it in green color, is going to be something like this. So this is like a cup, right? So this will extend all the way up towards infinity like this whole surface. And then we want to find this surface, y equals z. So this is your z-axis, this is your x-axis. So it's a little bit hard to draw here. I'll just draw this in red. So this will be a surface that's going to go like cut through this, like so this is going to cut this surface like this. So you have this green thing, and then this is kind of a surface that's going to go all the way down. Yeah. So this will be the surface. This is y equal, sorry, this is z equals x, right? So this will cut this um, green thing, green cup like thing. So this will look like, yeah. So let me actually show this if I can do that with the graph. No. Let's see. So I mean, let's work this out. So this sigma will be this cup-like shape. So it will be basically, this will be this cup-like shape, but it will be bounded by this red plane, right? So we will need to find a parameterization for this. Okay, so let us find how the parameterization would work. So looking at this, so let me write it in this form. The parameterization would be given like was, I'll just write it in xy form. So this is going to be xi, the x component, yi, and yj, and the z component, as you see here, is given by x squared plus y squared k. But this x squared, y squared cannot vary every time, everywhere. So it's bounded by x squared plus y squared and equals z equals x. If you work out this algebra, you will get that. I'm just uh, um, brushing this off because this is going to be a pretty big video if you just do simple stuff. So this will be a circle on the xy plane. So you cannot have, so the boundary is this. So if you just draw, so let me draw that for here instead. So I'm just now trying to draw the xy plane here. So the xy plane would be this x and y, and this is this circle here. It will have a center at 1/2, and 0. So the center would be over here, 1/2, and the radius would also be 1/2. R equals 1/2, right? So this will be the range on which this is. So, and since this is a surface that we are talking about, we should actually consider the whole region, right? So that means instead of equals, this will be working around this region, this whole region, right? So that is, the parameterization can be given in this form. But to make our computations easier, let me just erase this stuff. So we have actually done this. I'll reparameterize this. So this circle here is given by the circle here is given by the equation R equals cosine theta, right? And theta between negative pi over 2 and pi over 2, right? So this is the outer circle, I mean. So let me rewrite this parameter. So R, this vector, I can write it in terms of R and theta. So X will be R cosine theta I, plus Y will be R sine theta, if you're familiar with the usual circular coordinates, plus, so x squared plus y squared will be r squared. So this x squared plus y squared will be r squared k. And the bounds of each of these, so theta will be between negative pi over 2 to pi over 2, and then r will be from 0 to cosine theta. So that is this outer circle here, and r will be starting here, and it will move all the way from 0 to this point, which is r cosine theta, depending on the value of theta, right? So this is our basic framework. And we said that this should move in the counterclockwise direction, which is this. If you look at, if you take the right hand rule, it means that the normal should be upwards on the z direction, right? So upward. So let's keep this in mind. Z should work upwards. So we will talk where it will matter later on, right? So I think this part is fine. So let me just delete this stuff, and we can work out the integral. So I'll just erase this part here, just make space. And I think, let me just write this curl of f equals 2i minus j minus k, so that we just don't need to worry about that later on. So right, so now we just need to compute this sigma curl of f, and then this n is given by r. We need to find the derivative with respect to simple r, cross r we need to find the derivative with respect to theta, and then we have dr d theta, right? And the appropriate bounds over here. So the first thing we should do is find this one. So let me work that out first. So r. So just take the partial derivatives of this with respect to r. So once you do that, you have cosine theta I plus, let me just write this in the other side. So we just Z orientation direction. Right, you just make sure. So this is sine theta j plus 2 r k r theta equals, so we take respect to r, negative r sine theta I plus r cosine theta j, and so there's no theta here, so that's just 0k. We can just leave it out. And now we need to take the cross product of this. Theta, so sorry, this should be equals ij. Let me just write it out. Let me just this part. So ij k. So this I is r, so that is cosine theta, cosine theta, sine theta, 2r, negative r sine theta, r cosine theta, 0. Okay, let's work this out. So for I, you just multiply this and multiply this, take the difference. So we just have negative 2r squared cosine theta. I just work out the rest as usual, see what we get. Negative 2r sine theta j. We have a, okay, and then we, for that we have just r, right? So this is what we get for this. So we said that we need to have it in the positive z direction. So let's look at this, the cross. So this is basically your n, this one. So the direction of this is positive, the k direction of this is positive, so it's pointing upwards. So we are fine. So we just need to, if it was negative, we just need to flip the sign of this one and then use it here. So let's see what we get. So when we write down the limits of integration here, what we get here is, so first we write down theta because it is the independent one, negative pi over 2, and then we need to write limits of r, 0, cosine theta, and curl of f is this. So we have 2i minus j minus k, and now we take the dot product of this. So this is what we have, negative 2r squared cosine theta I minus 2r sine theta j plus r k dr d theta. Okay, let's write down this. Negative pi over 2, 0 cosine theta. So we get negative 2r squared cosine theta. So this should be 4 here. Plus 2r sine theta minus r dr d theta, right? Okay, so this is the integral that we need to deal with. Okay, so I think this stuff we don't need anymore. So I'll just erase this and then work the whole integral. Okay, so what we have here is negative pi over 2 to pi over 2 0 cosine theta minus 4r squared cosine theta. So no, there's no r squared here. It should be cosine, just cosine. So there's no square here. It's not supposed to be there. Yeah, I think it just wrote it wrong here. So we have negative cosine theta here, plus 2r sine theta minus r dr d theta. Okay, I'll just erase the rest below. So let me just quickly move through this. So when you do this inner integral with respect to r, what you will get is negative 2 cosine cube theta. Yes, I guess it's correct here. Yeah, and plus cosine square theta sine theta, and this will be 1/2 cosine square theta dt. Okay. So negative pi over 2. Let me just first work this out here. So cosine squared theta here, cosine squared theta sine theta. I can just simply write this as 1 minus sine squared theta cosine theta, sorry, sine theta here. So I will end up with sine theta minus sine cube theta, and cosine squared theta, I will write it as so I can write this as 1 plus cosine 2 theta over 2. And if you have these formulas, sine 3 theta is equal to 3 sine theta minus 4 sine cube theta, and cosine 3 theta is equal to 4 cosine cube theta minus 3 cosine theta. So I remember. So you just use these formulas here. So negative pi over 2, pi over 2, negative 2. This one is basically cosine 3 theta plus 3 cosine theta over 4. And over here you get sine theta minus sine cube theta. So we have sine theta. And for sine cube theta, I just write 3 sine theta minus sine 3 theta over 4. And for this, I write cosine squared theta, I just have 1 plus cosine 2 theta over 2 and d theta. So once you actually work this out, you will get something like this. Negative pi over 2, pi over 2. So we have negative 1/2 cosine 3 theta, negative 3 over 2 cosine theta, plus, let's see, 1/4 sine theta plus 1/4 sine 3 theta negative half negative 1/4 cosine 2 theta d theta. So I think this is pretty much easy to work this out. So this is just cosine 2 theta, this is cosine theta, sine theta, sine 3 theta. Oh, I think this should be 3 here. So sine 3 theta and this is cosine 2 theta. So I think this is easy to work. So I'll just out. So I'll just leave this as an exercise for you to do. So I think this was clear. And if you don't, if you find anything unable to understand, please write down that in the comment section. Okay, so bye.